Okay, so what is this .csv? It's an Excel file. It's a text file. And when you have two numbers, they are separated by a comma. Okay, so if you somehow open it from somewhere else, then you will see a bunch of numbers and bunch of commas. Basically, this is a text file from Excel. Now, so this is usually how you get your data set. So you download a data set or you make a data set in Excel and you save it in CSV, which is text. It doesn't have this unnecessary information. Very efficient, compact. So R usually opens the CSV file. Okay, you can open anything, but this is one of the convenient ones. Okay, so we have a directory in your computer, and we have a data set in that directory, right? Is it correct? Okay, remember the path of your directory, and let's open R. Now, what I'm going to do is very confusing, tricky. So listen carefully, okay? So this is the hardest part of computation. So the thing is that we have to tell R which directory you have to look for to find your data set, okay? Otherwise, R has no idea. A bunch of maybe thousands of directories in your computer, so you have to tell exactly what directory I'm talking about, okay? So that's our job. So click this. Click change directory. Now the directory you just made is in C. Because this is a public computer, it's kind of complicated. So click this user, okay? Because there are many users for your computer. I'm a little bit confused. Is it this? No, it is not. So choose the first one, HYU. Okay, so I think that's my directory. And then let's click this. And then the matrix is the directory I just made. And then type so basically this is the directory you have to tell R, okay? Click change directory. And then you basically have to find the directory you just created, okay? That's in C for me. Users, HYU. And this one, which is desktop in English. And then matrix is the directory I just created. The name of this directory can be different for you, right? If you said, for example, like Kim, then the directory name will be Kim. And type this. Okay, so your data is saved in A, capital A, right? Now, how many observations do you have? And how many variables do you have? So one method is to count them, but that's very inefficient. So for example, we can type this. So A is a matrix, right? So the number of row is the number of observations. And the number of variables is 18, okay? Or you can say this, number of rows. Or you can say number of columns, okay? So the matrix A has a lot of columns, a lot of variables, right? variable 1, variable 2, variable 3. It has 18 of them. So I'll think that it has 18 variables inside of this object A. Okay? So how do you find that which variable you have in your data set? So one method is this. So basically I just ask R to show me the first row. Okay? So the variable name just follows. Or you can say this. LS means list. So basically, you ask R to show me everything saved in A. Now let me talk more about this comment. One is that the name can be anything you want. So it can be, for example, like F. So why not? So F can be an object that you save your data. So it really doesn't matter. Or I frequently just call it data. So it's kind of confusing. But when I do that, data becomes a variable, an object in R that saves your data. Okay? So the name can be anything you want. So basically, when you read a data set into R, the function is read. Okay? So that's the function you have to remember. So when you want to read a data set, remember read. So what's the meaning of .csv? So this is a read function specifically for the CSV file, the Excel file. And then you have this quotation mark. Inside of the quotation mark, you have the file name. So that's what it is. Now let's try to understand this data a little bit better. So one variable we like to understand is a test score. This guy. So the test score is a sum of reading score and math score. Okay? Average of these two scores. So I like to know the mean, the median, and standard deviation of this test score. So how do I do that? Mean of. So I want to say test score, but it doesn't work. Why? Because the test score is a variable saved in other variable, like data or A, right? So you have to say the whole name. So there's an order, right? So there's this object, data, or it can be F, it can be A. And inside this object, there's a variable test score. So I like to use this data set variable and calculate the sample mean. Now, do you remember the comment for the standard deviation? SD. So the mean of the test score is 654, and the standard deviation is 19. Let me tell you this. Let me ask you this. So in this variable, the mean is 654, and one standard deviation is 19. So from the mean, if you go to the right and to the left by one standard deviation, what do you know about this? So this is plus 19, this is minus 19. Do you remember this empirical rule in statistics? So mean plus minus one standard deviation, you have about 2/3. Is he right? 2/3 of observation. I think that's correct. About 2/3. 2/3 of the scores are here, between here. So it's about 635 and 675. No, 673. So in this range, you have about 2/3 of the observations. Now, if you go 2 standard deviation away to the right and left, how many observations do you have? 95% of observation, right? So from the mean, if you add and subtract like 40 or 38, then you have about everybody. Almost everybody, not everybody. Things like that. So that's how we use the mean and standard deviation. Now, median and everything else can be calculated in the same way. One convenient function is summary. Or you can say histogram. So it shows the distribution of the test score. So this test score is the dependent variable. Usually, we just like to know what is the variations in the test score. And the important independent variable is the class size, which is the student-teacher ratio. Basically, this is the number of students divided by number of teachers, number of full-time teachers. So perhaps we can make a histogram for the ratio. So basically, we know that the mean and the median class size is about 20. So in this area, one class has about 20 students. The smallest one has 14 students, which is very small. The largest one has about 26. Now, what about the covariance between the test score and the student-teacher ratio? It's -8. What does it mean? What's meaningful for the covariance is a sign, right? It's negative. What does it tell you? They move to the other direction, right? So if you increase the class size, the test score usually goes down. Let's check. So the common plot, make a scatter plot. For the scatter plot, you need 2 variables. The first variable goes to the x-axis, and the second variable goes to the y-axis. Now you realize that this is not such a great choice. So let me change the order. So that's the relationship between the class size and the score. Are they negatively correlated? What do you think? One thing we do know that it's very noisy, right? So the R squared that we learned yesterday cannot be very high. There's so much variations in the dependent variable. Now you can make this plot, your plot, a little bit better looking. For example, if you say comma main gets so what does it mean? Inside of this plot, a function, if you say comma something, it means an option. So you specify an option for this plot. So main is an object, and main gets this as an input. Because these are not numbers but character, I need this quotation mark. So whenever I enter a character, I put them inside of the quotation mark. So let's check what it does. So what do you see? You see a title, right? So main option is for the title. Now when I say xlab, it means the label, the name of the variable in x-axis. So I have this label here, right? ylab means label the title of the variable for the y-axis. So I have this label here, right? So if you want to make it more colorful, you can change your color. Is red better? Let me show you something else. So this is another choice. Or maybe green. Oh, this is not that great. But anyway, you can change a lot of things in this common plot. Okay, let's go back. So far, I have to type a lot of these things, right? Data dollar. Because I have to convince R that this test score variable, str as a variable, they are saved in this object data, right? So that's why I need a whole path. This is a path for this variable. And after some time, it's kind of annoying that I have to type the whole thing. So if that's the case, you can attach your data. And the path is unnecessary. So what is happening here? Now suppose that this is a memory in R, okay? Although they are all the same, I have a data set A and a data set F and a data set data, right? Because I read the same data set 3 times with different name. But in some cases, sometimes you have to read 3 different data sets for different name, right? So that's why you need a path to make it very explicit, make it very precise, to R what you mean by the variable test score and STR. When you attach one of these, that becomes the default. Okay? So you don't have to tell that. You have to find the test score in this particular data set because that becomes just a default choice. That's the meaning of attach. Do you understand? So this guy becomes the default choice. So when you don't use any path, R understands that it must be saved in this data set data. Right? Not in A, not in F, but in here. Because you just attached it. Now if you don't like it, you can detach it again. Now the data, this data set is not the default choice anymore. So if you type the variable without any path, R does not know what to do. It needs a path because there's no default. But for today, let's just attach this data set. Now the main thing today is how to run a regression, right? The thing is, surprisingly, it's extremely easy. So let me just tell you how to write it. The function is lm. You say y tilde and x. So y means your dependent variable. So the order matters here. So your dependent variable is regressed on x, your dependent variable. So this is going to be the test score, and this is going to be the class size, STR, right? LM means a linear model, linear regression model. That's the meaning of LM, linear model. So there are a bunch of other comments like this. For example, if you type NLM, this is a function for a nonlinear regression model. If you say GLM, it's a function for the generalized linear model, things like that. Okay, so that's how it works. But this is the function we are going to use. So can you type it? Now, let's interpret the result. So you have minus 2.28 for the slope. What does it mean? You can say it in Korean. That's fine. Any volunteer? You want to try? This one, minus 2.28. Try? What does it mean? So if you increase your class size by 1 unit, which means one more students, right? What happens?
학생이 한 명 늘어날 때마다 테스트 점수가 2점씩 떨어진다는.
Good. So test score goes down by 2.2, right? Now if you reduce the class size by 1, what happens? The test score goes up by 2.2. Now what does this mean? 698.
Predicted test score when student-teacher ratio is 0.
So it's that is right. So we have data set about here, right? When the class size is between 16 and 26, 14 to 26, something like that, right? There's a bunch of data. And the regression line fit the data, it gets a result like this. Okay? Now, if you want to extend it to the other side, it's going to hit the point, and that will be 698. Okay, that's the y-intercept. So this is the value of y when x is 0. Now for this example, this is not such a meaningful number because around this there's no information. So we tend not to interpret things like this. So for this exercise, this is a meaningful coefficient. So that's how you run a regression. You want to try something else? So let's try math score. Or you can try reading score too. As a dependent variable. Now, if you decrease the class size by 1, what happens to your math score? It goes up by 1.9. What happened to your reading score? It goes up by 2.6. So on average, the average score goes up by 2.2, right? So somehow, if you decrease the class size, it's the reading score that you have a bigger effect. Is this something you can understand? You can explain? Did you expect something like that? So why that happens? Why reading scores goes up more than the math score? It's kind of mystery to me. I don't know why. So maybe some people can argue that for the math score, what matters more is not the class time or more attention, but maybe the student's ability or potential, things like that. For the reading score, the teacher's input may matter more. That can be one explanation, but honestly, I don't know how to explain it. Okay. So we have a bunch of other variables. What is this? This is the average income of the district. Okay, so if you wonder whether the average income explains the variations in the test score, you may want a regression like that. Okay, so why don't you try if you want to? So this can be new independent variable, and the dependent variable is the test score. Okay, the computer is the number of computers in school. So if you have more computers, maybe per students, then maybe the school is better equipped or has more budget. This one is the expenditure per student. Okay, so some schools are richer and some schools are poor. So if you think that this expenditure, how much you spend for students, explains the variations in the test score, you may want to run such regression. The test score as y, and this as x. Okay. Meal percentage. They have lunch, and when the family income is below certain average threshold, then you have some reduced rate. I'm not sure whether this is a free meal or just a cheaper meal, something like that. But some students has the reduced rate for the lunch. So it simply calculates the percentage of students who are on the meal plan. So if this percentage is higher, then on average the family of the district is poorer. Okay? So if you think that that really matters for the test score, you're going to run such a regression. And this is the class size. And there's a bunch of other variables. This is also important. This is English percentage. This is the rate of students who have to learn English. So basically immigrants. So they are coming from the immigrants family. So this variable matters a lot. For example, for the reading score, because they have to read the whole thing with a new language. Okay? So if there is some regression you want to run, maybe you can do it now. That's up to you. So let's say that your dependent variable is the test score, the average score, and you can choose your independent variable. Just check whether you have the result you can imagine. So did you run some regressions? Did you get the result you want? So basically that's how you run a regression. Let me tell you a few things, okay? Now, so you can run a regression and save it in an object, right? This is very useful. So you can make a plot, scatter plot. And you can add a line, a straight line, inside of your scatter plot, okay? Now it'll be better if I change the color. So it's a scatter plot. And AB line means A means intercept, B means slope. So basically it's just a straight line. So what I want to do is I make a plot and then I add a straight line. And the line is basically the regression line, okay? Now, can you add something else? Why not? So for example, oh, 650 is not such a good choice. So that's how you use an AB line function, okay? It basically tells the intercept and slope. So you can make quite pretty plots using this. And my second point is, A is an object you just created, and it saves everything that comes from this LM function, the regression function. R is some kind of minimalist. It doesn't want to show you a lot of information unless you ask them specifically. So right now, if you just type A, then it shows the intercept and slope. That's it. So if you want to know more, then you have to ask more. There's a lot of functions you can ask. One convenient one is summary. So if you say summary of A, the summary of this regression, then it has this table, right? But it has a lot more information. If you type ls A, again, A becomes an object, right? Because we just created in such a way. This is how I created A. Right? So LM produce a lot of information and save everything in A. So if I say list of A, it means show me everything in A, and these are the objects that is saved in A. So you can use them. Now, what is the coefficient, regression coefficient in A. So you have to type the whole path. But you don't have to type the whole words. R is efficient enough, you just guess. So what is the model I used? No, this is not. Do you remember what's the residuals? That's your prediction error, right? Do you remember the last example we proved? What's the claim there? Sum of residual must be 0, right? So let's check it. So how do you see the residual? So that's how you see the residual. UI hat for everybody. And then you have sum. So that's essentially 0, right? So that's the claim we proved. Now what is the next claim that you're supposed to prove for the assignment? The sum of UI hat is 0, right? But sum of UI hat times xi must be 0 too. Do you remember that? Okay, so let's check it. What is your x? That's str. So this is my one object, and this is my second variable. So what I'm saying is, your assignment, the homework problem is this, right? This is a residual from the regression, and this is a student-teacher ratio. So I want to show it empirically, computationally, the sum must disappear. So that disappears actually, becomes very small. Now, if I say 8, a fitted, this is the predicted value. That's yi hat. Okay. So what's my prediction for the first school district? What is my prediction for the first 10 school districts? Now suppose that you want to see the prediction for the last school district. Can you find it out without actually count anything? Think about that. How do you display the last value in this $8 fitted? So this is how you display the first value, right? It's a vector. So when you say 1, it means first element. How do you say the last element? So very uninteresting answer. It looks something like that. I somehow know that 420 is the last. But that's cannot be that good, right? Do you remember any function that gives the 420 as an answer? N low. How about that? Or dimension. Also gives an answer for 420, but dimension has two numbers. It's a vector, right? So here you can say for example, so again, if you type list of A, then there are a bunch of information you can find out. And as I said, the summary is another function. So what summary does is it takes this information, so the coefficient, residuals, fitted value, predicted value, and everything else, and then it starts to calculate a lot of different things, right? And then make this table. But you can also save the outcome of the summary in a different variable, b, and you say, show me everything in b. Do you remember the r squared? Okay, so that's how you get the r squared. The 0.05. What does it mean?
5% variation in dependent variable is explained by regression.
So the 5% of the variations in test score is explained by the regression. And we are going to learn these different things. What is the adjusted R squared? We're going to learn it later. What is the sigma? We're going to learn it later. What is the F statistics? We're going to learn those things later. Now, there's a lot of interesting variable. So some of you may want to know the effect of class size. Then you can run such a regression and have your answer. And if you like to know the financial background of the family, and then you can, for example, use this as an independent variable and get your answer. Now, can you combine them? Can you run a big regression that has everything you want to see? So that's, of course, possible. You can simply add them. Now, if you add the effect of the financial background of the family, then somehow the class size, the effect of class size becomes different, right? So why? Why this is the case? Things like that will be the main topic for the class that's coming. But for a while, you can just do the experiment, and you simply keep adding your variable, okay? And you can expand the regression. So something like that is called a multiple regression, a regression with many independent variables. So that's the result when I use 4 independent variables. What happens to my r squared? Now the r squared is here in the table. What's the value of the r squared now? 0.8. Now what does it mean? It was 0.05, 5%. Now it's 0.8, 80%. What does it mean? How much variations in the test score is explained by the regression? 80%. Okay? So 4/5 of the variations are now explained. So when you use the class size alone, it explains 5%. But these 4 variables put together explain 80%, which is a big improvement, right? Now, how to interpret this, which is a better model, things like that. Again, this will be a very important topic for the class. I think that's it. That's all I have to say today. Do you have any questions about this regression thing now? Now, one thing though, now you are ready to do your homework, okay? So be sure that you do your homework, work together, help each other, okay? That always saves time. And then I'll see you on Tuesday. And by the way, the quiz on Wednesday, you should be able to do at least run a very simple regression, because that's the question in the assignment, in the homework.